Hello, so let's try physics paper 4 of the 4-1 variant, October-November 2023, code 97002. So let's start with question number 1. State what is indicated by the direction of the gravitational field at a point in a gravitational field. So basically, whenever a test mass is placed inside a gravitational field, it is directed towards the source of that field. So it's the gravitational field lines, the direction of gravitational field lines just represent the direction of the gravitational force acting on a unit mass or a test mass inside the gravitational field. So it's the direction of gravitational force acting on a test mass or a unit mass, whatever we call it, inside the field. Explain with reference to gravitational field lines why the gravitational field near the surface of the Earth is approximately constant for small changes in height. So now if we look at a big picture, the field lines are radial and they are pointed to the center of the massive body. So if we look at the big picture, they point at the center of the massive body. However, when we look at the when we zoom in at the surface, these same radial lines appear almost parallel to each other. Why? Because there is a huge difference between the small changes in height at the surface and the radius of the planet. So radius of the planet is very, very high as compared to small changes at the surface. So that's why the gravitational field strength appears almost constant for small changes in height at the surface. If if we go in a significant fraction of the radius of the planet upwards or outwards, then we will definitely see a change in gravitational field strength significantly. So with reference to gravitational field lines, so first off we have to state that radius of the planet is very large compared to the height, small changes in height. Radius of Earth is very large compared to small changes in height at surface. So gravitational field strength as represented by approximately parallel lines is roughly constant. A large uniform sphere has mass m and radius r. Point P lies on a straight line passing through the center of the sphere at a variable displacement x from the center. So as you can see, the displacement is outwards from the planet. Figure 1.2 shows the variation with x of the gravitational field G at point P. due to the sphere for values of x for which P is inside the sphere. The magnitude of the gravitational field at the surface of the surface of the sphere is y. Determine an expression for y in terms of m and r. So we know that y is the maximum field strength at the radius of the planet, m is the mass, r is the radius. So we can use the formula for g, which is the gravitational force per unit mass, F over m. So this can be rewritten as g m over r squared. But since we need the y at the radius r, so we can rewrite that as y equals to g m over r squared, where g is the universal gravitational constant. This is very important because they have already said identify any other symbols that you use. So it's a good habit to state the meaning of any symbols that we use in our answers. Explain why the surface of the sphere G always has the opposite sign to x. Now the sign of this G, which is the direction of the field lines, is towards the center of the massive body, like towards the center of the planet. X was if we look at this, so X is going outwards, but the direction of the field lines is towards the center of the planet. That means the sign on the G is opposite to X because they're opposite, basically. The directions are opposite. So direction of G, or the gravitational field strength, or just simply the gravitational field, always acts towards the center of the body. So gravitational field, or the gravitational force, you can say, field lines point to the center of the planet as gravitational field is attractive. Sorry, this is double T. And this direction is opposite to x as x is positive outwards from the planet. Complete figure 1.2 to show the variation with G, variation of G with x for values up to plus minus 3r, for which the point P is outside the sphere. Okay, all right. So we know that the gravitational field strength would be reducing with this. So at at the double the radius, the G would have reduced by G would be gm over 2r whole squared. So this would be gm over 4r squared. So this is 1 over 4th of y. Similarly at 2r, so at 3r, that would be 1/9 of y. So 1 over 4 is 0.25 y, and 1 over 9 is roughly 0.1. So let's see, and on both sides. So 0.25 at 2R, so this is 0.25, and 0.1 would be somewhere over here, and right over here also, so 0.25 somewhere over here, and 0.1 over here. So we will draw a smooth curve for this. Let's go for this, and so this is it. Question number 2, define specific heat capacity. So heat capacity of a substance, specific heat capacity of a substance is the quantity of heat required to raise the temperature of a unit mass by unit temperature. By 1 unit temperature. By a unit temperature also. Heat, another word we can use is thermal energy. Instead of heat, we can use thermal energy, but we don't use heat energy because heat means thermal energy. So no need to use heat energy. An ideal gas of mass 0.35 kg is heated at a constant pressure so that its internal energy increases by 7,600 joules. During this process, the volume of the gas increases from 0.38 meter cube to 0.63 meter cube, and the temperature increases by 56 degrees Celsius. So show that the magnitude of work done on the gas is 5,000 joules. So work done is P change in volume. So since it is heated at a constant pressure, that's why. So 210 raised to power 5 times by change in volume is 0.063 minus 0.038. So 210 raised to power 5 multiplied by 0.063 minus 0.038. So that is 5,000 joules. Explain whether the work done on the gas is positive or negative. So since the gas is expanding, it is the work is done by the gas. But when we talk about work done on the gas, it is negative. So since the gas is expanding, as the gas is expanding, as the gas is expanding, against external pressure or against atmospheric pressure, it's doing work against external pressure. So work done on the gas is negative. So work done by the gas is positive, but work done on the gas is negative. So it's just a matter of words. Determine the magnitude of thermal energy Q transferred to the gas. Now transferred to the gas, we have to use the change in internal energy, thermal energy, and change in work done. So the change in internal energy was 7,600. We want to find out what's the change in internal energy. And the work done on the gas was negative, so that's minus 5,000. So this means that the change in Q, or the small q, however we want to call it, it's 7,500 plus 5,000. So that is 12,500 joules. Calculate the specific heat capacity of the gas for this process. So we know that Q is equal to mc delta T, or mc delta theta, whatever you want to call it. This Q is equal to change in heat provided. So mass of the gas, oh sorry, we need to find out the specific heat capacity. So first let's make C the subject. So that is delta Q divided by M times by change in temperature. So that is 12,500 divided by mass. We need to find out 0.35 kgs. Okay. And the change in temperature is 56 degrees. So divided by 0.35 divided by 56. So this is 637.8. Since the data is given to us in two significant figures at most, so 630, let's call it 640. And the unit, we can see that this is joules, kg. Change in temperature, although we took in degrees Celsius, but if you know the differences between Celsius and the Kelvin, we know that 1 unit of Kelvin change is equal to the 1 unit change in Celsius. So we can say per Kelvin over here. So joules per kg per Kelvin. Okay, so on to the next. Oh, sorry. The gas in B is now heated at a constant volume rather than at constant pressure. The increase in internal energy of the gas is same as in B. Use the first law of thermodynamics to explain whether the specific heat capacity of the gas for this process is less than, same as, or greater than the answer in B4. Right. Okay. All right. So when they say that the increase in internal energy of the gas is same, and since this is ideal gas, the change in internal energy of the ideal gas is almost approximately equal to the change in kinetic energy of the gas, which is directly proportional to the temperature rise, basically. So this means that if the increase in internal energy of this ideal gas is same as previously, that means the temperature rise is also the same. So temperature rise is the same as plus 56 degrees Celsius. Secondly, we have it's now heated at a constant volume. That means there's work done is P change in volume. Since change in volume is 0, therefore no work done. Right? So this means that when we construct this Q plus W, This part is 0, and this part is same as before, 76,000, 7,600, sorry. Now, the change in heat, or the heat required, heat input, is directly affecting the internal energy. So there is no loss of energy by work due to the work done by the gas. So since change in energy is the same, 7600, and that is equal to, again, mc delta same T now. So before this, in the part A, sorry, in the previous part, sorry, we had 5000 that was turning into mc delta T. So now the delta T are the same. The determined energy that is being input is more, so that means C is going to be more than that previously. So uh, 0.35 times by 56. So this is going to be significantly more than the 5000 over 0.35 times by 56 that we did. So, all right, let's put it into words. Okay, so since there is no change in volume, there is no work done on or by the gas. The the internal energy increase, the increase in internal energy is same as before, which indicates same temperature rise or same temperature change. Therefore, the change or the increase, or sorry, the heat therefore the thermal energy is directly affecting internal energy. So specific heat capacity would be more than before. Okay, all right, moving on. The product PV for an ideal gas is given by PV is equal to 1 over 3 nmc squared. State the meaning of the symbols N. N is basically just the number of molecules, so number of molecules or particles of the gas. M is the mass of one particle or one molecule, mass of a single molecule or particle, sorry, molecule or particle, whichever one you want to use. C squared, this is average C squared or mean squared speed of particles or again molecules. Use the equation of state for an ideal gas to show that the average translational kinetic energy of a molecule of the gas at thermodynamic temperature T is given by EK is equal to 3 over 2 kT. Okay, so since we know that this PV, since this is an ideal gas, PV is equal to NKT, and this is, as above, it shows that this is also equal to 1 over 3 nm mean squared speed. So these two are equal to each other. So if we cancel out the n's, we are left with kT is equal to 1 over 3 mass root mean squared. Now the kinetic energy is the half mv squared basically. So we take 3 on the other side, that becomes 3 kT is equal to m squared, and since ek is equal to half mv squared, we need half mc squared equal to 3 over 2 kT. And that's it, yes. Okay. The surface of a star consists mainly of a gas that may be assumed to be ideal. The molecules of the gas have a root mean square speed of 9300 meters per second. The mass of a molecule is 3.34 10 raised to the minus 27 kgs. Determine to 3 significant figures the temperature of the surface of the star. So we know that, okay, so we will use the above formula over here, half m c squared is equal to 3 over 2 kT. So t can be cancelled. T would just simply be m c squared divided by 3k, where k is the Boltzmann constant. So this is equals to mass of one molecule, 3.34 10 raised to the power minus 27. Speed is 9300 squared. 3 and the Boltzmann constant. Boltzmann constant value we can check from the table given. So Boltzmann constant is 1.38 10 raised to the power minus 23. 23. Okay, so let's calculate this. 3.34, sorry, 3.34 times by 10 raised to power minus 27 times by 9300 squared divided by 3 times by 1.38 times by 10 raised to power minus 23. So mass square speed 3k. So this comes out to be 6977 Kelvin. So we can round it up to 2 or 3 significant figures. So this is roughly about, let's do 3 significant figures because we have 3.34. So 6980, or even if we do 7000, I think that would be okay. The radiant flux intensity of the radiation from the star is 2.52 times 10 raised to the minus 8 watts per meter squared when observed at a distance of 4.16 10 raised to the power 16 from the star. Calculate the luminosity of the star. So we know that radiant flux intensity is just the amount of radiant energy or radiation that passes through a given surface area on Earth per unit time per unit area. So that's luminosity divided by 4 pi d squared, where d is the distance of Earth or the observer from the star. So we need to find the luminosity, that this is just F times by 4 pi d squared. So radiant flux intensity is 2.52 10 raised to power minus 8 times by 4 pi, distance is 4.16 10 raised to power 16 whole squared. So we get 2.52 10 raised to power minus 8 times by 4 pi times by, that's right, 4.16 10 raised to power 16. So this is 5.48 10 raised to power 26. Now what will be the units? So this is watts per meter squared and this is meter squared. So this is just watts basically. So 5.48 10 raised to power 26 watts. Okay, determine the radius of the star. Now for the radius of the star, we will use the Stefan-Boltzmann law, which states that the total energy radiated per unit surface area of a black body across all wavelengths per unit time is directly proportional to the fourth power of the black body's thermodynamic temperature. So that is 4 pi r squared sigma T raised to power 4, where sigma is the Stefan-Boltzmann constant. So we know the luminosity, we need the radius, so r would be, let's do the r squared first. So L over 4 pi sigma T raised to power 4. So luminosity is 5.48 10 raised to power 26 divided by 4 pi. Temperature we figured out was 6,980 raised to power 4 times by the Stefan-Boltzmann constant. Let's check the value. Sorry, that is 5.67 10 raised to power minus 8. Okay, so let's see. So 5.48 times by 10 raised to power 26 divided by 4 pi divided by 6980 raised to power 4 and divided by 5.67 10 raised to power minus 8. That's it. So we get 3.24 10 raised to power 17 meters. So 3.24 10 raised to power 17 meters. No, this was the square, sorry, this was the square, where we need to take the square root. We get this value, 5.6, 569 10 raised to power 6, or when we go further, this will be 5 point, let's go with 5.7, or let's go 5.69, and 3 significant figures is also fine, 10 raised to power 8 meters. Okay, all right, never mind. The gas at the surface of a star has a very high pressure. Use the basic assumptions of kinetic theory to suggest why, in practice, the gas at the surface of the star is unlikely to behave as an ideal gas. So we know, so in the kinetic theory of an ideal gas, we know that the particles are uh, far apart from each other, which basically means low pressure. So this is one point, and because they are very far apart from each other, the interactions are only limited to collisions, and there are negligible intermolecular forces in between them. And since uh, they're also far apart from each other, the volume occupied by the particles themselves is very negligible as compared to the volume of space they occupy in general, as a whole. So since we say that uh, particles are very close to each other due to high pressure, so the intermolecular forces would be not negligible, and the volume of molecules would also be not negligible as compared to volume of gas. Okay, all right. Let's move on. Okay, so question number 4. A heavy metal sphere of mass 0.81 kg is suspended from a string. The sphere is undergoing small oscillations from side to side. The oscillations of a sphere may be considered to be in simple harmonic motion, simple harmonic with amplitude 0.036 and a period 3. So amplitude is 0.036, t is 3.0 seconds. State what is meant by simple harmonic motion. So simple harmonic motion is a motion in which acceleration is directly proportional to its displacement from a mean or fixed position and is always directed towards that point. So a motion in which acceleration a is acceleration acceleration of body is always proportional to its displacement from a fixed point, from its displacement x from a fixed point, and is always directed towards it. A directly proportional to minus x. Now, The reason why we were able to do this because we already introduced a and x. If we just write it without explaining what a and x is, we might lose marks. Otherwise, we don't need to write it if we have written all of it. Calculate the angular frequency of oscillations. So angular frequency omega is 2 pi over t, or 2 pi f. So that's 2 pi over 3. So 2 pi divided by 3, that is 2.09 radians per second. All right. Since we have two significant figures, so let's just use 2.1. The total energy of the oscillation. So total energy of the oscillations is given by half m omega squared x naught squared. So half m omega was the 2 over 3 pi whole squared, and x naught was, amplitude was 0.036 meters. Okay. Squared. So squared times by 0.036 squared. Mass was let's see what the mass was. Mass was 0.81 kgs. So times by 0.5 times by 0.81. So that is 2.3 10 raised to the power minus 3 joules. So we will write 2.3 10 raised to the power minus 3 joules. Okay, the suspended sphere is now lowered into water. The sphere is given a sideways displacement of plus 0.36 from its equilibrium position, and then released at time t is equal to 0. The water causes the motion of the sphere to be critically damped. Sketch the variation of the displacement x of the sphere from its equilibrium with position with t from t is equal to 0 to t is equal to 6 seconds. So critical damping goes like, either it goes like this, oh sorry, not at 0, it goes like this, sorry, it decays to like this, or it goes a little bit like this and then goes like this. So it's up to us how we can draw this. So it starts at plus 0.036, so this is 0.03, 2, 4, 6, this is 0.036. Like this. So question number 5. Define electric potential at a point. So electric potential at a point in an electric field is just the work done to move a unit positive charge from infinity to that point. Two isolated charged metal spheres x and y are situated near to each other in a vacuum with a centers a distance of 24 meters apart. Okay, point P is at a variable distance x from the center of the sphere x. That means this is the sphere x, center of the sphere x. Line on the line joining the centers of the spheres. Okay, shows the variations in the x of the electric potential V due to the spheres at point P. State three conclusions that can be drawn about the spheres from 5.1. Conclusions may be qualitative or quantitative. Okay, so we know that V is equal to KQ over R, and depending on the charge, the potential could be positive or negative. So if the potential is negative over here, this means this is negatively charged, and this is positively charged. This is X, this is Y. What else can we draw a conclusion about? So another conclusion that we can draw from this is that for X, the radius is 2 meters and the Y has a radius 2. So this is also an observation. So let's write down the observations that we've yet. So X is negatively charged, and Y is positively charged. Okay, radius of Y is twice that of X. Now let's see any other conclusion that we can make about this. Let's think about the charges. Let's think about the charges. So the radii are, so let's, their potentials are roughly, so the potential of Y is roughly half of that of X. So let's see what that means. So Vx is approximately half of Vy. So basically Vx has KQY2, let's call that 4, sorry. Let's call it 4. And that is equal to approximately half of K Q, sorry, it's the other way around. That's the half over here. Oh, sorry, half of X, half of X. Sorry, this is Vy, half of X. I was right before, sorry, Qx, and that is 2. So let's establish a connection between them. So K gets cancelled. This is 4. This is also 4. This is also Qx. So yeah, so that means the Qy is approximately equal to Qx. So as we can see, this is not exactly equal, because if that was exactly equal, it would be over here. But these are approximately equal to this. So charges, the magnitudes of charges on X and Y are approximately equal to each other. Okay, a positively charged particle is placed at a point P in D such that x is equal to 12 meters. The particle is released. Describe and explain the subsequent motion of the particle. So it is over here. So this is a positively charged particle, so that means it will be attracted towards the negative, repelled from the y. And what else? As the distance clears up, so the gradient dv over dr is basically, sorry, the negative gradient of this potential graph indicates the strength of electric field. So if the gradient is decreasing towards the left, towards the x suddenly, that means the electric field is increasing. So if the electric field is increasing, that means force on that charge is increasing. So we can state that also. It it will be attracted towards x as it moves closer to x. Its acceleration will increase. This is indicated by a significant change in potential towards x, since electric field strength is proportional to potential change in potential. The attractive force on charge increases as it moves closer towards x. Okay, all right, moving on. Okay, so question number 6, define magnetic flux density. So we can use this over here, F over IL formula over here. So this is the force experienced per unit length of a conductor in a magnetic field per unit current when placed perpendicular to magnetic field. We can also say magnetic field direction, but that's fine also. Electrons are moving in a vacuum with a speed of 1.7 10 raised to the power 7 meters per second. Electrons enter a uniform magnetic field of flux density 4.8 millitesla shows the path of electrons. The path of electrons remains in the plane of the page. State the direction of the magnetic field. Now, this is done using the Fleming's left-hand rule. So the direction of electrons is equal to uh, the opposite of conventional current, which is towards the left. So the direction of current that we have to take is opposite. The force direction is downward, so this means that the B field is into the page. So into the page. Okay, all right. Show that the magnitude of force exerted on each electron by a magnetic field is this. So force is equal to BQV or BEV basically. Where V is the velocity. So the magnetic flux density is 4.8 millitesla. Charge is 1.6 10 raised to power minus 19. V velocity is 1.7 10 raised to power 7. Okay, all right. So on the other side we have 4.8 times by 1.6 times by 1.7 10 raised to power minus 3 minus 19 plus 7, that is equal to 1.3 10 raised to power minus 14 newtons. On figure 6.1, draw an arrow to indicate the direction of centripetal acceleration of the electron when it enters the magnetic field at point X. So it's directed inwards, centripetal acceleration. Use the information to calculate the distance d between the path of electrons entering the magnetic field and the path of the electrons leaving it. Okay, all right. So since this follows a circular path, this will be the radius of the curvature. This will be the radius, so we want twice that of the radius. So we know that this BQV is equal to the mv squared over r. So we need the r, that is equal to mv squared over BeV. So m, the mass of the electrons. So mass of the electrons, let's check the data sheet over here. Mass of the electrons, 9.11 10 raised to the power minus 31. So 9.11 10 raised to the power minus 31. Velocity was 1.7 10 raised to the power 7 whole squared divided by this 1.3 10 raised to the power minus 4. Sorry, this is minus 40. So let's do this. 9.11 times by 1.7 times by 1.7 divided by 1.3 times by 10 raised to the power minus 31 plus 14 plus 14. So we get 0.02 meters. Since d is equal to 2r, so 2 times by 0.02, that is 0.04 meters. Okay, so the electrons are placed with positrons that are moving with the speed of 3.4 10 raised to the 7 along the same initial path as electrons. The positrons enter the magnetic field. Point X. Draw a line to show the path of the positrons through the magnetic field. Okay, so they have given us the speed of the positron, so we can find out the radius of curvature over here. So BEV part, so they have the same positive, they have the same magnitude of charge, but their velocities are different, right? So let's find out. So for the r squared, we figured out that that was equal to mv squared over BEV. So this is, we can cancel one out into mv. So mv, so mass of positrons is almost the same, so 9.11 10 raised to the power minus 31. Velocity is 3.4 10 raised to the power 7, 1.3 millitesla. Sorry, 1.3. Sorry, was it 1.3? 4.8 millitesla. Sorry. And magnitude of charge is same, 10 raised to the power minus 19. So 9.48 times by 3.4 divided by 4.8 divided by 1.6 times by 10 raised to the power minus 31 plus 7 plus 3 plus 19. That is equal to 0.04. So r squared is 0.04, and the square root of that will be 0.2. So as we can see, this is roughly 2 times by that of the what we had for the electrons. And it makes sense because the speed of the positrons is twice that of the electrons. So we can also show it another way. So r squared is mass is the same as the electrons. V is just twice that of the electrons, and BE as the same. So if we say m over BE was just r squared as before, so the 2v basically would be just 2r, let's call it r prime, so that would be 2r squared, sorry, 4r squared. And that would mean that the radius of curvature, new radius of curvature, would be 2 times that. And that also means if the radius is doubled, this means that the diameter will be twice now, basically. So it will be, new diameter will be twice the old one. So the positrons will enter over here. They will have a larger curvature, and they will enter. Oh, sorry. Let's draw this again. They will have a larger curvature and will enter out. So this is 2D. They will enter over here and pass out like this. Okay, so now question number 7. A varying current I passes through a resistor of resistance R in the circuit shown. Figure 7.2 shows the variation with time t of I. The current has magnitude 2I naught when it's in the positive direction, and I naught when it's in the negative direction. The period of the variation of the current is t. Okay. Determine the expressions in terms of I naught and R for the power dissipated in the resistor for the times when the current is in the negative direction. So in the negative direction, the power will be, we know that it's I squared R, but in the negative direction, this is I naught. So this is I naught square R. Similarly, the current, when the current is in the positive direction, again, power is equal to I square R. So I is 2 I naught square R, which is 4 I naught square R. So one thing to notice, this and this one, the second one in the positive direction, this is 4, sorry, this is I squared. This is 4 times more power dissipation in the as in the negative direction. Okay, so on figure 7.3, sketch the variation of P with T between T is equal to 0 and T is equal to 2T. Label the power axis with an appropriate scale. Okay, all right. So in the negative cycle, the power dissipation is I naught square R, and in the positive cycle, we have 4 times that. So we basically have to choose a scale, the vertical scale, such that it reflects it so. So let's say 1, 2, sorry. So this is, let's say this is 1, 2, 3, 4. Yeah, we can do that. So between 0 to 0.5 t, this is going to be this. This. And this is going to be the case after 1 also. At 1 to 1.5 also. Okay, all right. And then from between 0 to 0.5 to t, 1t, and then 1.5 to 2t, this is 4 times by that. So if this is I naught squared r, this is 2 I naught squared r, 3 and 4 I naught squared r. So this means that this is the fourth one. So this is the power dissipation. Okay, use your answer in B to determine an expression in terms of I naught and R for the mean power in the resistor. So for the mean of any function, so basically what we do is we sum up all the values, or we take the area under the graph and divide it by the total time. So what we do is we take the total area, so this is 1 over t, mean power is equal to 1 over t times by the area, which is I naught square r times by t, half of t, plus we have 4 I naught square r for another half t. So let's see how this how that comes up. So 1 over t, so this is t and t, all the t's get cancelled out. So we are left with I naught, all the t's get cancelled out. So we have I naught squared r, I naught squared r, 1 over 2 plus 4 times by, 2 times by 2 is 4, so this. So this is 2 and a half, 5 over 2. So 5 over 2 I naught I naught squared R. The root mean square RMS current in the resistor. So the mean power, the relationship between mean power and the RMS current is basically I RMS squared times by R. So mean power is due to the, it's also due to the I RMS times by V RMS also. So that way, but we have the RMS squared that we calculated out. Sorry, that's what we need, but we have the mean power that we calculated out. So mean power is 5 over 2 I naught squared R is equal to I squared RMS times by R. So R and R get cancelled. So I squared RMS is equal to 5 over 2 I naught squared. So I RMS should be equal to I naught times by root 5 over 2. So yeah, so I naught root 5 over 2. So this is 5 over 2 I naught squared R, and power, this is 4 I naught squared R, I naught squared R. Right, okay. Okay, moving on. Question number 8. Show that the momentum P of a photon of an electromagnetic radiation with wavelength lambda is given by this. Right, okay. So we know that the energy of a photon is equal to hc over lambda, and that is also equal to the mc squared, the Einstein's equation. So when we cancel out 1c each, this part over here, this is the momentum. So we have already shown this. So therefore P is equal to h over lambda. Use the expression in A1 to show that a photon in free space that has a momentum of 9.5 10 raised to power minus 28 is a photon of red light. So red is somewhere around 700 nanometers of wavelength. So if we can show the wavelength in that region or around that region, we can show that it's a red light. So for the lambda, we need to find the lambda, that is going to be h over p, Planck's constant. So we need to go see the value of the Planck's constant. So we go look into the data sheet. Planck's constant, that is 6.63 10 raised to power minus 34. So 6.63 10 raised to power minus 34. Momentum is 9.5 10 raised to power minus 28. So over here we have 6.63 divided by 9.5 times by 10 raised to power minus 34 plus 28. So that is equal to around 6.97 10 raised to power minus 7, which is equal to 697 nanometers. So yes, so red, so since 697 is approximately equal to 700, we can even write it as 700. We can already just round it up to 700 nanometers. So therefore it's a red photon. Therefore photon is of red light. Okay. A beam of red light light of intensity 160 watt per meter squared is incident normally on a plane mirror as shown in the figure 8.1. The momentum of each photon in the beam is 9.510 raised to the power minus 28. All of the light is reflected by the mirror in the opposite direction to its original path. The cross-sectional area of the beam is 2.5 10 raised to the power minus 6 meters squared. Show that the number of photons incident on the mirror per unit time is this. Right, okay. So we know that this intensity is equal to power over area, and power is basically just energy over time, area. And in the photons, this is n, since we have number of photons. So n hf, or regarding the f, we have c over lambda. So h c t a lambda. So we need to find the number of photons per unit time. This is this n over t basically. So if we isolate n over t, this becomes I a lambda over hc. So we go, intensity is given as 160 watt times by cross-sectional area, that is given as 2.5 10 raised to power minus 6. Lambda was 700 10 raised to power minus 9. H is 6.63 10 raised to power minus 34, and C is 3 10 raised to power 8. So let's make sure the values are correct. 2.5, 1.4, okay, all right. So let's round it up. So 160 times by 2.5 times by 700 divided by 6.63 divided by 3 divided by, no, now times by 10 raised to the power of minus 6 minus 9 plus 34 minus 8. So we get 1.4, 1, and 10 raised to the power 50 per second. Use the information B1 to determine the pressure exerted by the light beam on the mirror. Okay, so for the pressure, we know that the pressure is equal to force over area, and force is basically rate of change of momentum over rate of change of momentum with respect to time. So we need to find the rate of change of momentum first. So rate of change in momentum, since the photons were reflected by that same speed in the exact opposite direction, so the change in momentum would be 2 times by mc basically. So mc was the previous momentum, so we could also write it as 2 times by h over lambda basically, or the momentum that we already had, basically 9.5, that was given 9.5 10 raised to power minus 28. So just 2 times by that. So 2 times by 9.5 10 raised to power minus 8 or plus 8, minus 28. Okay, minus 28, and over time was per second. Okay, so we're doing it per second. So in 1 second, basically. But we also know that in 1 second we have 1.4 10 raised to power 15 photons attacking. So the total momentum would be will be multiplied by 10 raised to power 1.4 10 raised to power 15 per second also. So we just need to calculate this. 2 times by 9.5 times by 10, 1.4, 10 raised to power minus 28 plus 15, that is 2.66, 10 raised to power minus 12. So this is change in momentum over change rate of change of momentum, basically meter per second squared. So divided by this area, so pressure would be 2.66, 10 raised to power minus 12. So this is in newtons, as we can call it. Area, the cross-sectional area that we used, that was 2.5, 10 raised to power minus 26. Sorry, minus 6, sorry, minus 6. Minus 6. So divided by 2.5, 10 raised to power minus 6, we get 1.1, 10 raised to power minus 6 pascals. So this is 1.1, 10 raised to power minus 6 pascals. Okay, so the beam of red light in B is now replaced with a beam of blue light of the same intensity. Okay, so just to explain whether the pressure exerted on the mirror by the beam blue light is less than, same as, or greater than the pressure exerted by the beam of light. Okay, so if the intensity is the same, IR is equal to IB, but we have NR over T, where we had the expression for the intensity, HC over A lambda, HC over A lambda R is equal to N blue HC over A lambda B. So we know that H is the same, C is the same, area is the same. So basically it's the game of, let's call it the blue over the number of photons of number of blue photons per unit second per unit time, and the number of red photons per unit time. So after we cross multiply, this is equal to lambda b, that means the wavelength of B over lambda r. So basically it's a ratio. So this means that we know that the lambda blue, the wavelength of blue is smaller than lambda r, because its frequency is greater. So this means that the number of photons, or number of photons of blue light, will also be lesser now, because as you can see, these are directly proportional to each other. So since the number of blue photons per unit second incident on the beam, incident on that cross-sectional area, will be less, by that same ratio, that, let's see what that means basically. So we said that they are, if they have the same intensity, let's see what if they have the same intensity, this means that their What will it affect? So let's see how that affects the rate of change of momentum first. So we said that the momentum, where did we write this? Did we write somewhere? No, okay. So we know that the change in momentum of the photons going back, being rebounded, was 2 v, or basically 2 hc over, h over lambda, basically h over lambda. So the change in momentum, as we can see, is greater, the change in momentum, uh, this will be the general formula, but since lambda blue is smaller than lambda r, when we take the reciprocal, 1 over lambda blue will be greater than 1 over lambda r. So if we compare the change in momentum, so that will be 2h over lambda b, but that will be greater than 2h over lambda r. That means change in momentum will be greater for the blue photons than it was for the red photons. However, the story is not finished yet. Over here, we also use the number of photons also. So the number of photons was being affected by that same ratio. So the number of photons, we were actually multiplying that for the rate of change of momentum. So we actually did 2h over lambda b multiplied by nb over t divided by time. So basically we were doing the per unit time. So 2h over lambda b times by, when we take the ratio that it becomes, that is lambda b times by, so nb, when we cross multiply, that becomes lambda b over lambda r times by nr over t. So lambda b gets cancelled. This ends up being 2h over lambda r times by number of red photons per unit time. Now, as you can see, this is exactly the rate of change of momentum for the red photons, right? So since they are incident on the same cross-sectional area, the cross-sectional area is the same. So this means that the pressure exerted by the blue photons will be the same as that of the red photons. So now let's use English to translate this all maths now. Now I've shown you the math and the reasoning behind it. Let's see, let's write it in words now. So blue photon beam will have more momentum and will exert will have greater change in momentum but since number of photons will be lesser, so force exerted will be the same. So rate of change, the total rate of change of momentum will be the same. Therefore, the pressure exerted will be same as before. Okay, all right, moving on. All right, so state, question number 9, state what is meant by nuclear fusion. Now, nuclear fusion is when two smaller nuclei fuse together into a heavier nucleus with the release of energy. So let's write it. This is the process of combining two lighter nuclei into a heavier nucleus with the release of energy. Now, this part is very important to write. Never forget that. On figure 9.1, sketch the variation of binding energy per nucleon with nucleon number A. So it actually goes like this. If we want to make a smoother curve, somewhat like this, but it actually does have spikes over here somewhere. So the peak will be over here at 56, and yeah, that's it. Okay. On your line, the point X that could represent a nucleus that undergoes an alpha decay. So an alpha decay would be over here, a heavier, more unstable nucleus. Point Y that represents a nucleus that undergoes nuclear fusion somewhere over here. So, no. X, and somewhere over here, Y. Closer, more closer they are to the this region over here, the more they're likely to do that nuclear fusion. Okay, all right. Nucleus Z undergoes nuclear fusion to form strontium and xenon. According to this table, 9.1 shows the binding energies of strontium 93 and xenon 139 nuclei. This is binding energy. Okay, these are binding energies. Okay. The fission of 1 mole of xenon, nucleus Z, xenon is Xe, releases 1.77 10 raised to the power 13 joules of energy. Okay, determine the binding energy per nucleon of Z in mega electron volts. Okay, all right. So let's see, what do we need? Okay, so the binding energy released, this is not the binding energy released, actually this is the binding energy released. So binding energy released, let's call that binding energy released, is basically the difference between the binding energies of the products and that of the parent. So basically what we will do is we will take the difference between the binding energies of the products and subtract that with the parent, which is unknown at the moment. So let's add them up. So binding energy of the strontium, Sr, plus binding energy of xenon minus that of the binding energy of Z. Since we're finding the binding energy of Z first, so what we will do is the binding energy of strontium, xenon, minus that of the released. So 1.25 10 raised to power minus 10 plus 1.81 10 raised to power minus 10, 10, minus the energy released 10 raised to power 13. So, this is the total binding energy for 1 mole. So we need to divide this by the Avogadro's constant to find the energy released for 1 nucleus. So 6.02 10 raised to power 23. So we will do 1.25. Actually, since the powers on the two are the same, so we can add them up. So, sorry, we can lump them up. 1.25 plus 1.81 times by 10 raised to power minus 10 minus the whole. Let's do this again. So, we have 1.25 plus 1.81 times by 10 raised to power minus 10, and then minus that with 1.77 divided by 6.02 times by 10 raised to power 13 minus 23. So we get the total binding energy is 2.76 10 raised to power minus 10 joules. But since we need that for the nucleon, so we need to find the total nucleon of Z. So the mass numbers are conserved. So we have 1 plus, let's call that A over here, mass number of Z equals to 93 plus 139, and the 2 neut neut neutrons. So mass number of Z would be 93 plus 139 plus 2 minus 1, that's plus 1. So that's 233. So binding energy per nucleon. So binding energy per nucleon of Z will be 2.76 10 raised to power minus 10 divided by 233. So let's find out the binding energy per nucleon. So this is 2.76 divided by 233 times by 10 raised to power minus 10. This is 1.18 10 raised to power minus 12 joules. We need to convert that into electron volts by converting it into electron volts in electron volts. We do 1.18 10 raised to power minus 12 joules divided by 1.6 10 raised to power minus 19. So divided by 1.6 10 raised to power minus 19, we get 74. This 74. So since we need it in megajoule, so this becomes 7.4, roughly 10 raised to power 6 joules. Oh, sorry, electron volts. So this is 7.4 mega electron volts. Okay, all right. Moving on. Ultrasound and X-rays are both types of waves that are used in medical diagnosis to form images of the internal body structures. Complete table 10.1 to state for each type of wave the method of production of wave, whether the wave that is detected and used to form the image is the wave that has been absorbed, reflected, or transmitted by the internal body structure. Method of production is the oscillating quartz crystal. And the decelerations of electrons on metal. Detected wave. Whether the wave that is detected and used to form the image is the wave that has been absorbed, reflected, transmitted by the internal body structure. Yes, okay. So ultrasound is reflected from the body structures, and the X-rays, how we detect, is the absorbed, the transmitted one. Okay, so for one type of wave passing through the tissue, the wave has 72% of its initial intensity after it has passed through 6.2 centimeter of the tissue. Calculate the linear attenuation coefficient mu for the tissue of the wave. So for the linear attenuation, we have I is equal to I naught e raised to power minus mu x. I over I naught ratio, they have given us 72%, so that is 0.72. That is equal to e raised to power minus mu x, where x is the depth. So since this is an exponential equation, we will use ln 0.72 is equal to minus mu 6.2. So mu will be ln 0.72 divided by minus 6.2. So ln 0.72, divided by minus 6.2, that is equal to 0.053. Another wave of the same type as in B1 passes through 9.3 centimeter of the same tissue. Calculate the percentage of initial intensity that is attenuated by that tissue. So I is equal to minus mu x. So we need I over I naught equals to e raised to power minus 0.053 times by 9.3 centimeter. So e raised to power minus answer times by 9.3, that is 0.61. So this translates into 61%. So 61% is the transmitted intensity. So the attenuated will be 100% minus 61%, that is 39%. So 39%. Okay, all right. And that's it. So see you guys in the next paper. Bye bye.